This presentation consists of 5 main sections. First, we will provide an introduction to the topic. Next, we will present the problem statement and discuss the given question. After that, we will explain the problem solutions by showing the methods and calculations used to obtain the answers. We will then complete the presentation by summarizing the key points discussed. And finally, we will provide the reference that were used in completing the assignment. Okay, now let us begin with the introduction. So the first one, the introduction of the differentiation, is a fundamental concept in calculus that measures the rate of change of a function with respect to a variable. It is used to determine the slope of a curve and has many applications in science, engineering, and economics. Common techniques of differentiation include the power rule, product rule, quotient rule, and chain rule. These techniques help simplify the process of finding derivative and solving various calculus problems.
Okay, so for question 1, I will explain the meaning of differentiation and 3 differentiation techniques that we have learned. Okay, differentiation is a method in calculus that helps us understand how a quantity changes in relation to another quantity. In simple terms, it is used to find the rate of change of a function and the slope of a curve at a particular point. This concept is very important because it is widely used in fields such as science, engineering, economics, and optimization problems. There are 3 main different techniques, which is first, the product rule. This rule is used when a function is formed by multiplying two functions together. Second, the quotient rule. This rule is applied when a function is written as one function divided by another or in fraction form. Third, the chain rule. This rule is used for composite functions where one function is contained inside another function. So in question 2, we are required to differentiate the following functions with respect to x, which are given in part A and part B. So how do we solve this question? For part A, we are given the function y equals 5x cubed times e to the power of cos x. Since the function consists of two functions being multiplied together, I will use the product rule. First, I differentiate 5x cubed using the power rule. The derivative of 5x cubed is 15x squared. Next, I differentiate e to the power of cos x using the chain rule because the exponent contains another function which is cos x. Let u equals cos x. The derivative of e to the power of u is e to the power of u multiplied by du over dx. Since the derivative of cos x is negative sin x, the derivative of e to the power of cos x becomes negative e to the power of cos x times sin x. Now, I apply the product rule, which is u prime v plus u v prime. Substituting the values, we get dy over dx equals 15x squared times e to the power of cos x plus 5x cubed times negative e to the power of cos x times sin x. After simplifying, we obtain dy over dx equals 15x squared e to the power of cos x minus 5x cubed e to the power of cos x sin x. Then I factor out the common factor, which is 5x squared e to the power of cos x. Therefore, the final answer is dy over dx equals 5x squared e to the power of cos x times 3 minus x sin x. For part B, we are given the function fx equals ln 5x over sine 2x. First, I apply the logarithmic rule. Ln A over B equals ln A minus ln B. So fx becomes ln 5x minus ln sine 2x. Next, I use another logarithmic rule. Ln AB equals ln A plus ln B. Therefore, ln 5x can be written as ln 5 plus ln x. So the function becomes ln 5 plus ln x minus ln sine 2x. Now I differentiate each term. The derivative of ln 5 is 0 because it is a constant. The derivative of ln x is 1 over x. For ln sine 2x, I use the chain rule. Let u equals sine 2x. Using the formula, the derivative of ln u is 1 over u times du over dx. Derivative of sine 2x is 2 cos 2x. So derivative of ln sine 2x is 1 over sine 2x times 2 cos 2x. Since there is a negative sign in front, it becomes negative 2 cos 2x over sine 2x. Substituting everything, we get f prime x equals 1 over x minus 2 cos 2x over sine 2x. Using the identity, cot theta equals cos theta over sine theta. So 2 cos 2x over sine 2x becomes 2 cot 2x. Hence, the final answer is f prime x equals 1 over x minus 2 cot 2x.
Okay, now let's move on to the question 3. Given y sine 2x minus ln 2y equals to 2x squared plus 3, find dy over dx using implicit differentiation. How to solve it? To solve this question, we differentiate both sides of the equation with respect to x. First, for the term y sine 2x, we apply the product rule because it consists of the product of two functions which are y and sine 2x. Let u equals to y and v equals to sine 2x. The derivative of the y is dy over dx, and sine 2x, v equals to sine 2x, we use 3-go rule. So the derivative of the sine 2x is cosine 2x, d over dx to x, and it becomes 2 cosine 2x. And we apply to the product rule, and we will get 2y cos 2x plus sine 2x dy over dx. Next, we differentiate the term natural logarithm of 2y. By using the logarithmic differentiation rule, the derivative of ln u is 1 over u du over dx. Since u equals to 2y, the derivative of 2y is 1 over 2y, 2 dy over dx. We eliminate the number of 2, and it becomes 1 over y dy over dx. The third one, we use the power rule. The formula of the power rule is d over dx, s to the power of n equals to ns to the power of n minus 1. We apply the number of 2x squared plus 3 into the formula. Therefore, the derivative of 2x squared is 2 multiplied by 2x raised to the power of 2 minus 1, which simplifies to 4x. Therefore, meanwhile, the derivative of the constant term 3 is 0, since the derivative of any constant is 0. Hence, the derivative of 2x squared plus 3 is simplified 4x. Now that we have successfully evaluated the individual derivative using the logarithmic rule and the power rule, and product rule, and also product rule, So now we can substitute them back into our primary implicit equation. This gives us the combined expression located right here at the bottom. 2y cosine 2x equals to plus sine 2x dy over dx minus 1 over y dy dx equals to 4x. Looking closely at this structure, our main objective is to solve for dy over dx. To achieve this, we need to group all terms containing dy over dx on the left side and move any non-dy over dx terms over the left-hand side. Notice the blue transition arrow showing that the independent term 2y cosine 2x, we will be subtract from both sides to shift it over. Let's see how this rearranged on the next slide. Moving on to the left slide, we perform two actions simultaneously in the first row. First, on the left side, we factor out the common term dy over dx from the remaining components, leaving us with sine 2x minus 1 over y inside the bracket. Second, as indicated by the arrow from the previous slide, we successfully moved 2y cosine 2x to the right side by subtracting it. This leaves us with the clean rearranged equation dy over dx sine 2x minus 1 over y equals to 4x minus 2y cosine 2x. To fully isolate dy over dx, we divide both sides of the equation by the entire expression inside the bracket, which is sine 2x minus 1 over y. This results in the fraction shown in the second row, which is dy over dx equals to 4x minus 2y cosine 2x over sine 2x minus 1 over y. However, we cannot leave our answer like this because we have a complex fraction containing a nested fraction, specifically 1 over y terms in the denominator. To make this mathematically elegant, we need to eliminate that y from the bottom. So to clear the fraction in the denominator, the most direct mathematical strategy is to multiply both sides, both the entire numerator and denominator, by y. As written in blue color, multiplying by y over y is equivalent to multiplying by 1. So it keeps the value completely unchanged. In the third row, you can see this operation clearly set out. We wrap the top and bottom in bracket and place y outside to prepare for distribution. And finally, distribute y into every single term. In the numerator, multiplying 4x by y gives us 4xy, and multiplying 2y cosine 2x by y gives us 2y cosine 2x, 2y squared cosine 2x. In the denominator, distributing y to sine 2x brings us directly to our absolute final answer. dy over dx equals to 4xy minus 2y squared cosine 2x over y sine 2x minus 1. The expression is now fully simplified, elegant, and perfectly resolved. Thank you.
So as for question 4, it states that to use linear approximation to estimate the value of fourth root 15.98 minus 2 over square root 15.98, correct to 3 decimal places. So, to solve this problem, we need to build a general formula. We have to replace the specific value of 15.98 with the variable x so that we can define our function as fx equals to fourth root of x minus 2 over square root x. We must do this because we cannot differentiate a static number. To prepare this function for differentiation, we rewrite the radicals as fractional exponents using power laws. This gives us our working as fx equals to x to the power of 1 over 4 minus 2x to the power of negative 1 over 2. As for step 2, we need to find the derivative f prime x, which gives us the rate of change for our approximation. By applying the calculus power rule to each term, the first term becomes 1 over 4x to the power of negative 3 over 4, and the second term simplifies to positive x to the power of negative 3 over 2. Writing this back into standard fractional form gives us our derivative formula. F prime x equals to 1 over 4x to the power of 3 over 4 plus 1 over x to the power of 3 over 2. Now, for step 3, we need to choose an ideal baseline point, x, for our approximation. We want a whole number very close to 15.98 so that it easily works with fourth roots and square roots, so we choose 16. Our given target value, x, is 15.98. To find our change in x, or known as delta x, we subtract 16 from 15.98. Therefore, it gives us an increment of exactly negative 0.02. As for our final step is to use the linear approximation formula, which is fx plus delta x equals to fx plus delta x multiplied by f prime x. First, we have to substitute our numbers to get f16 minus 0.02 equals to f16 plus negative 0.02 multiplied by f prime 16. Next, we expand this by writing out the full functions with 16 plugged in. On the left, we have our original function, and on the right, we have multiply negative 0.02 by our derivative function. Once we calculate all of this, it simplifies to f 15.98 equals to 1.499, which is our final answer. So to conclude, different differentiation techniques are suitable for different types of questions based on what each problem requires. Therefore, it is important for us to understand the main concept of each differentiation techniques as well as how to apply them in our working to solve mathematical questions efficiently.